Good. So, in today's agenda, we have to deal with the two major aspects, right? First, we will try to complete what I promised during our discussion. Ki, we would first deal with the matter of cluster analysis. Okay, and in this cluster analysis we will first get introduced with the concept of what is cluster analysis. Okay, and in this introduction we would try to see ki bhai, what is the purpose of cluster analysis, and uh, procedurally, you know, the main objective of doing this cluster analysis would be like, we would be starting our session with three objectives. The main three objective of today's session would be to learn कि भाई how you can interconvert data between NAMD and Gromacs. Okay, so this is major objective, right? So is it possible for anyone to use the data generated in NAMD, and can the analysis be done in Gromacs, right? So okay,
Yes.
is it interpolatable? That is what I want to say, right? Second is that once we convert the NAMD data into Gromacs compatible or readable files, what we will do is that we would try to see as to how to use the trajectories that are generated using NAMD and perform the cluster analysis using Gromacs. Okay, and next we will see कि भाई how is that you interpret the cluster analysis data, and what is that is exactly to be presented in your research paper. Okay, so let us first begin with the question as to what is it exactly, when we say that we want to do cluster analysis. So what is exactly cluster analysis? Let us try to define cluster analysis first. Okay, so basically cluster analysis is needed to be done on say some trajectories that you might have obtained using either NAMD or Gromacs. Okay, so this cluster analysis of trajectories obtained from MD simulations, well, you can say that it is a technique used to group similar conformations or snapshots of molecular systems based on their structural features and temporal proximity. Okay, so the primary goal is to identify distinct conformational states, or what we call it as clusters, that the system visits during the simulation. That is the main objective of cluster analysis. Okay, so this analysis is essential for understanding the dynamic behavior or structural transitions and functional aspects of biomolecule, right? So this is what we call it as structure analysis. Now let us think कि भाई what is the purpose of, you can say, cluster analysis. Purpose of cluster analysis. Okay, so in this context we would try to address ki like, what is the need to perform cluster analysis of trajectories obtained from MD simulations. Okay, so I would just list out a few applications of why is that it is necessary, or why is that it is of interest, or why is that it is important to perform cluster analysis of MD simulation. So the very first and foremost application of cluster analysis is, you can say, identification of conformational states. So you can identify the various conformational states using cluster analysis. Let me write it down this thing first. Identification of conformational states. So what is exactly that I mean when I say that cluster analysis can be used in identification of conformational states? So just to put it simply, cluster analysis helps in identifying distinct conformational states or structural motifs that a biomolecular system explores during the simulation. Okay, and obtaining such an information is crucial for understanding the dynamics and function of biomolecules, you can say, right? So second application can involve identifying the structural diversity in the dynamics of any trajectory. Okay, you can see that structural diversity identification. Okay, so what is that is involved in structural diversity identification? Now to explain you this, well, let us say that MD simulation usually generate a very large amount of data, and this data represent the dynamic behavior of molecular system over time, right? Everyone might agree with it, right? So this cluster analysis help identify distinct conformation or structural states that the system explored during simulation. Okay, so well, say for example, if you try to visualize a trajectory, it seems that everything is continuous, right? And in this continuous state of system, well, you can group you can group your conformations of the conformations of various states of your protein into various, you can say, categories. Okay, so while doing this clustering, well, this is very crucial for understanding the structural diversity that a protein ligand complex can take, and it can also give you an idea about how flexible that protein ligand complex is. Okay, and the third and most important you can say application of this cluster analysis involve something called as reducing the dimensionality. Okay, by using cluster analysis you can reduce the dimensionality of the problem. Okay, so what I mean is that this MD simulation generate very vast amount of data, and cluster analysis might help in reducing the dimensionality of data by grouping similar conformations in a group, and therefore provide a very concise representation of essential structural features. Well, this can be one of the application of structural performing the cluster analysis. And the next application that I'm going to talk about is the one that we would be interested in this particular tutorial or this particular session as such. Okay, so we would be performing cluster analysis for extraction of representative structure. Okay, so what is exactly the extraction of representative structure? Okay, so when we perform structure analysis, we usually end up in cluster centers, or sometimes these cluster centers are also called as medioids. Okay, so these theoretically these medioids can serve as representative structure of each cluster, right? And these representative structure thus provide insight into the most common conformation or the state visited by that system very frequently. Okay, so these representative structures can be used for further analysis or even the starting point for more focused simulation as such. Okay, so the thing is, the idea of extracting a representative structure is to know that among all the frames that are present in your trajectory, is there any frame that represent the entire simulation? That is what is interested when we perform cluster analysis and we say that we want to extract a representative structure. तो representative structure यानी क्या रहेगा? A state of your protein ligand system that you can say is a representative state of the entire simulation. Okay.
Yes.
And the last and most important one of the application you can say is that you can sample the rare event. Okay, so देखो, the thing is that when we perform MD simulation, of course we might miss some rare events due to finite sampling that we usually perform when we do MD simulation as such. Okay, so cluster analysis can aid in identifying and characterize this very rare event, such as you can say transition between protein states in ligand receptor interactions. We'll say for example, so well you can imagine that in MD simulation a very few of the conformational in very few of the conformational state or in very few of the trajectories the protein acquires certain conformation, right? And in majority of the frames it might have some another conformation, right? So in this way we can say that in this way if we have two clusters that we have identified, we can say that our protein can remain in two conformational states. One of them is very rare and another one is very common. But the point is, my friends, that you can detect कि okay, our protein ligand complex can remain in two conformational states as such, and these things can be analyzed using the cluster analysis data. Okay, so
Yes.
this is are a few application of cluster analysis, right? So in today's video, as I have already told you, we will learn three important things. First, we would learn interconverting data between NAMD and Gromacs. Second, we would learn how to use trajectories that are generated in NAMD and perform cluster analysis using Gromacs. So we are talking about the interpolability of the data between NAMD and Gromacs, right? And next and final thing is that we would see how is that we interpret the results obtained from cluster analysis, and what is that you need to focus when you present that data in your research paper. Okay, so the protocol per se that we are going to use today, that will say for example have 5 steps. Okay, so since we are using NAMD as a base configuration, base trajectory file, and we tend to or we want to use Gromacs for our cluster analysis, right? So first we need to convert the trajectory file that is present in DCD format to Gromacs compatible format. Maybe we will convert into XTC format. Okay. Second thing, if you want to, if you want to use anything in Gromacs, you would need a structure, right? The structure file in case of NAMD is PSF file, as we have already discussed, but the structure file in case of Gromacs is a GRO file. Okay, so what we need to do is that we need to create a structure file or what we call as GRO file from your PSF file. So once we have this GRO file and XTC file, you can easily work in Gromacs, right? Because that is what is needed. Okay, then there is an issue of renumbering that I will tell you later on. that this is something that is needed to be done, because during conversions of trajectory from DCD to XTC, it by default uses 0 as a starting point. So we will come to this point in a while. And finally, the fourth step would be performing clustering. And finally, to figure out what is to what we call it as to extract the representative structure, this step can be done using frame extraction. Okay, so this is what it is going to be today, right? First we would convert the trajectory file into Gromacs compatible format, then we convert the PSF file into Gromacs compatible format, then we would renumber the frames that are present in our trajectory, then we would perform clustering, and then we will see as to how do we extract the representative frame from the clustering results. Okay, so this is how we are going to work today. Okay, यहाँ तक समझ में आ गया है what is that is going on?
Yes, sir.
Okay, so let us begin. तो पहला वाला काम करेंगे अपन, to convert the DCD file to XTC file, right? well, देखो वैसे technically काफी simple है, but I will just let you know. And today we are going to use a new software called as Vega ZZ for doing the first two tasks. ओके जो कन्वर्जन का काम है वो सब अपन वेगा ZZ में करेंगे, राइट? सो लेट अस ओपन दिस वेगा ZZ. ओके, so in the example that I am showing you today, we will learn performing cluster analysis of a protein ligand system, and we will be starting with cyclooxygenase 2 enzyme that is complex with inhibitor flavonoid called as 2-hydroxyflavonone. Okay, so the thing is that we have simulated this system for 50 nanosecond. The trajectory that you would see is of 50 nanosecond, and we have its PSF in form of we have its structure file in form of PSF file, right? And of course I will have it in form of this ionized.psf, right? So ionized.psf is the PSF file that I would be working on with, right? So it will not show over here that anything has happened, right? But trust me that we have opened this ionized.psf file, right? So first we need to convert this PSF file into GRO file. Okay, so since we have loaded it shows over here loading explore PSF file. That is what it says, right? Then go to file, right? And simply use this save as option. And in this save as option, currently we have PSF format. It has detected it properly. All we need to do is to convert it into uh, Gromacs, Gromos or Gro file as such. ठीक है?
Yes, sir.
Right? So let us give it a same name, ionize.grow, and save it. Right? So next thing is that we also want to convert our trajectory into Gromacs compatible file. Right? तो उसके लिए we need to go to this calculate, and then in analysis the trajectory analysis window opens up, right? So we need to browse to the trajectory file 7HFN centered. This is the trajectory file we have, and we need to open it. Okay, so once we have opened it, we no longer need this trajectory analysis window anymore. So let us close it, and now let us save this trajectory into Gromacs compatible form, right? So for doing this, we would go to this file and use this save trajectory option, right? And you can rename it with an appropriate name so that you can later on recognize it. Okay, so by default it has detected that it is DCD file, which is right. We want to convert it into Gromacs XTC format, right? And let us keep the same name, ionize.xtc, right? And hit this save button. Now it will start to convert everything, saving frame by frame into our new XTC file. So once this is done, we can close it. So for time being we need to be patient till all the 1000 frames are done, right? So once this is done, we will no longer need this Vega ZZ anymore. So let us close this thing. Okay, so now we have saved the trajectory file in XTC format and structure file in Grow format. Let me show you as to what we have done, right? So we have saved this file. I will show you in properties that this is the Grow file, ionize.grow. We have created it from PSF file, right? And this is ionize.xtc file. This is a trajectory file that we have converted it from DCD. So we have now two Gromacs compatible files, right? Structure file and the trajectory file. And we are now ready to roll and work in Gromacs. Okay. So let me close this thing. So now what we will do is that for subsequent analysis, we will use Gromacs, and specifically in this case, in our case, we will use program Grovin in our demonstration. Now let me introduce you that Grovin is Windows version of Gromacs that is developed at my own lab, right? So if you don't know how to install Grovin on Windows, then maybe you can check out a separate video, right? So I will show you where that video is. Okay, you can simply check it out. You can search for go to maybe YouTube video, YouTube. Okay, or maybe I will simply show you it on sourceforge.net. Okay, so sourceforge, if you go on sourceforge.net and search by Grovin, you will come to this page, and simply you can download it using this button, download button, right? And once you download it, you can go to my channel, Scribbles in Bioinformatics, right? And you can see a playlist over there, browse to playlist, and there is a playlist called as Gromacs on Windows.
Dyson's new all-in-one vacuum now washes hard floors too.
So you can use this video.
Joint pain can be a hurdle in your journey, so give it a long-lasting care. The new Hansaplast Active gives you 360-degree support and comfort for long-lasting pain relief. Hansaplast Active for long-lasting pain relief.
Okay, so here is the video to use this. So you are time being you can simply see this video for present above Windows 8. How do you download Gromacs and install Gromacs, right? So if you follow the steps correctly and install your Gromacs in program files, then there would be no problem. And once you install it, you will have the the icon over here as it is shown, like Gromacs. Okay, and when you double click this Gromacs, you might open it in a separate you can say separate command line version as such. Okay, so the thing is that this is what we are going to use, right? So when we work in Gromacs, the first thing that you usually do is you change the working directory. And how is that you change the working directory? We'll do the usual thing that we used to do in NAMD, right? We will copy the path of the working directory and simply use this cd command and paste it. Now since the working directory when you initiate a Gromacs is in C drive, so all we have to do is to use this cd command, as the desktop folder is already on C drive. Therefore we don't have to change any drive over here. So if your working directory is say in some another drive like D drive or E drive, then you might have to change the drive and then navigate to the working directory. But since we are doing on desktop, we don't need to change the drive, right? Okay, so now we are in test. Let us use this dir command to see if all the files are there in the working directory, right? So in this test folder we have all the files that are supposed to be there. Okay, so now I have already written the commands that we are going to use in this commands txt notepad file, right? So all you have to do is that you have to copy these commands, so okay, and paste it over here. So this is the first command that we are going to use, and let me tell you what is it and why is that we are doing this, right? So here we are, right? We have completed the conversion of DCD to XTC. We have also converted the PSF file into GRO file. Okay, now we have to do this renumbering thing, right? And how is that we do renumbering thing and why is that we need to do this renumbering thing, ये मुझे अभी आपको बताने का है पहले. Okay, so the thing is that one of the drawbacks of using Vega ZZ for format conversion is that while you perform that format conversion, the frame number in the converted trajectory is lost. Okay, so therefore we need to renumber each and every frame in XTC so that we can use it in further clustering procedure. Okay, so for renumbering, of course, there is a command in Gromacs called as traj conv. Okay, so this traj conv command can be used for renumbering the renumbering the frames that are present in your trajectory. Okay, so now let me tell you as to what is that it is present in this command. Okay, so this gmx will tell that you are supposed to run Gromacs. Traj conv command is the command that we are going to use for uh, renumbering the frames in your trajectory. This dash f will give you or you can say this dash f is used for providing the input XTC file, okay, or any input file in Gromacs. Dash o will give you an idea as to what will be the name of the output file. Okay, we will name our output file as renumber.xtc, right? And dash t0 indicates starting time default value. Okay, so uh, well say for example we are indicating that the starting time default value is supposed to be 0, that is we are starting the simulation at 0, right? And the initial frame would be numbered as 0, and that dash time step indicate what is the last frame in our trajectory. So all in all, what we are giving over here, that what is the first frame and what is the last frame, right? Trajectory numbering always begins with 0, that you should always remember. Okay, is it clear?
Yes, sir.
Okay, So next what you need to do, when you give this command, just hit enter, and over here as you can see the renumbering of the frame has already started. Okay, so it won't take much of the time, right? And after this thing is done, a new XTC file has been created, and this new file is called as renumbered.xtc, and in this trajectory file there are all the frames renumbered appropriately. Okay, so now next what we need to do, तो ये भी हो गया अपना, we are done with this renumbering stuff as well. Now we will begin with the major and important step that we are trying to do today, what we call it as clustering, right? So for clustering we have got this command. All you have to do is to copy this command and paste it over here, right? So since I have also selected an enter, it kind of executed. Now let me tell you as to what is it that we have done when we gave this command, right? We provided this command, like we have used this gmx cluster. Cluster is the command that we are going to use. Okay, so this command is for it says that Gromacs use cluster command, and this cluster stands for clustering. Okay, then we have used dash f, wherein we are providing the input file with the name renumbered.xtc that we have just generated a while back, and then we have providing the structure file, that is by giving this dash s icon. Structure file is in form of ionize.grow that we have created from your Vega ZZ. Okay, next we have to provide the log file. Okay, dash g. Okay, dash g cluster log is this particular command will tell as to this will specify where to save the log file. Okay, and this is very important, my friend. We are providing a cutoff of 0.11 nanometer. Okay, this 0.11 is, you can say, an RMSD cutoff. Okay, so it is like saying that include a frame in a cluster if it has got the RMSD of 0.11 nanometer. That is what it means, right? And once you execute the command, then it will ask you as to what is that you want to use in clustering. Okay, so let us kind of uh, perform clustering on the backbone atom. Okay, and the command, or you can say the menu for clustering backbone atom is at position number 4. So all you have to do is to select 4 and hit enter, and the clustering will begin considering the RMSD value around your backbone atoms, and the frames will be saved in a given cluster if it has got the RMSD value below 0.11 nanometer. That is what is going on in the background. Okay, now all you have to do is to wait for a while till all the clustering thing has been done. Okay, so it won't take much time. Now it says that it has found 2 clusters, right? And a new file might have been created called as cluster.log. So basically this clustering step generates 3 output files. One of them would be an XVG file, another would be an XPM file, and another would be the log file. This log file is the one that we are interested in. Okay, now as you can see that if you open this log file, you can see that this Gromacs has figured out that there are 2 clusters in the trajectory. Okay, so it is like saying that all of these frames that are present in this particular section can be you can say, can be grouped into cluster 1. and all the remaining frames can be grouped into this cluster 2. Okay, so total there are 54 frames in cluster 1 and 946 frames in cluster 2. Okay, so now based on this data, you can clearly say that your protein might have, you can say, two conformational state. One conformational state is present in as per this cluster, and another conformational state as per this bigger cluster as such. And majority of time your protein ligand complex remains in this particular conformation that is represented by this cluster number 2. Okay, so this is exactly what this log pi means. Okay, now the representative frame of the first cluster, as you can see in this particular location, is the frame at time 9990 picosecond, right? And the representative frame of this cluster is at this particular picosecond, right? So this number is very important for us, because this is what we are going to need for frame extraction, that is next step. Okay, so this is what it is. So this middle RMSD is the name, or you can say is the time frame in your simulation where the representative structure was observed. Okay, so this particular number 609390 correspond to the frame at 609390 picosecond, which is observed as a representative frame for this particular cluster. And my friends, this is the frame that we would be interested in. Okay, so now let us think of as to how is that we can extract this particular state of the protein from the trajectory, right? And for doing that, we would be performing the next step, that is called as frame extraction. So we are done with clustering. Now we begin with frame extraction. Now we have identified, okay, that the frame at this particular picosecond of time is the frame that is supposed to be the representative frame of this cluster and eventually our trajectory.
Yes, sir. Sir, this is like when we wanted to go from NAMD to Gromacs. पहले conversion अपन ने किया, फिर अपन ने cluster analysis कर लिया. सर, suppose अपन ने Gromacs में ही सब कुछ run किया है.
हाँ, तो फिर if you have that XTC file, then go ahead.
Okay, और सर grow file कौन सी वाली use करेंगे?
Grow file initial वाली use कर सकते हैं आप, जो पहले बनाई वाली है.
पहले मतलब NPT वाली या NPT
फाइनल वाला,
अच्छा प्रोडक्शन वाला, प्रोडक्शन
हाँ,
वाला.
हाँ.
ओके ओके, गॉट इट.
ठीक है. Okay, try out using Gromacs if you already know, right?
Yes.
So now let us think of how do we extract this representative frame. Okay, so for extraction you can use another command that I have already prepared over here, what we call as traj conv command, right? So let me simply paste it. Okay, so now let me tell you as to what is there in this traj conv command. So this Gromacs traj conv command, we are providing this -f, that is mandatory because the program needs to know what is the input file. So the name of input file is renumber.xtc. -s will give you the structure of the structure of your system, that is ionized.grow. Okay, so -o will give the name of the output file. We will give the same number as an output file, so as we would later on remember okay, this is the number of frame that nth number of frame that we are interested in. And this -dump will specify what frame from the XTC file is to be extracted. Okay, तो इसे यहाँ पर अपने को वो नंबर देना है. Okay, the number that we have observed here as a middle RMSD frame, right? So this is the same number that you are supposed to provide over here. Right, all you have to do is to hit enter, and now it will ask you what is that you want to save, right? So the thing is that we need to save everything in the frame to be present in the output PDB file. Okay, we want to save everything: water molecule, the protein molecule, the ligand molecule, if there are any ions, right? Everything we want to save it in a PDB file. And such a kind of option is to select this zeroth group. Okay, so in other words, the entire system is needed to be dumped, and for doing so we can select this zero option. Okay, the first option. Okay, so this first option will save the entire system at that particular time frame, right? So if we give 0 and hit enter, now it will go to that specified trajectory time, and it will dump the frame at time step 609390 picosecond, right? And it will save it as the output file that we have named it over here. Okay, so this is the state of your system at 609390 picosecond time, which is our representative pose or representative frame. Okay, so now what we need to do is that we need to edit it. Why? Because we won't be interested in that water molecule when we perform analysis, right? So we are interested in only protein ligand when we analyze or when we perform interaction analysis, right? So what is the point of keeping that water molecules in it? So what we will do is that we will remove all the water molecule, right? Or we can also remove the sodium atoms or any ions that are there. Okay, we would focus only on protein ligand system, right? Let us delete it, right? One more thing that you should know is that the termination line over here is at a wrong location. The termination line usually indicate the end of protein data, so let us put it where it belongs, and let us kind of give this end line which indicate that the data of PDB file is over. So this is the right format of a good PDB file, right? So let us save it. And once you save it, let us close this thing. Okay, now let us think of as to how is that we evaluate the trajectory. Okay, or how is that we you can say how is that we analyze this uh, this analyze this clustering data. Okay, so what we usually do is that this frame would correspond to the most representative frame in the simulation, right? So now let us create a 2D representation of this 2D representation of the active site of this particular frame as such. Okay, तो उसके लिए let us open it in Discovery Studio. Just wait for a while. What we will do is that we will compare the whatever results that we have obtained from trajectory analysis, or whatever results that we have obtained from cluster analysis with the starting frame, or you can say with the docking frame that we have obtained. You know, we usually uh, we usually begin simulation with the docking results, right? So now what we will compare as to what exactly happened when simulation took place, right? We would compare it with the initial state of our system, that is the docking output. Okay, and how is that we do it, I will tell you. Okay, so once we open the, let me change the mouse mode. Okay, once we open the clustering result in this Discovery Studio, what we will do is that we will try to prepare a 2D representation of the active site. Rishabh? Huh? Oh, huh. Okay, okay, okay. ओके ओके, लगता है ये बंद हो गया। ठीक है, मैं फिर से लगाता हूँ। ओके, हाँ।